Today I'd like to talk about how to use the basic transistor as a switch, so let's get right into it. First off, why would you want to use a transistor as a switch? Why wouldn't you just use a switch itself? Well, if you have a device that can only output a limited amount of voltage and or current, and you want to activate a single or multiple devices that require more voltage and or current, faced with a dilemma. This is where the transistor can come to the rescue. Transistors are semiconductor devices with three leads. A very small current or voltage at one lead can control a much larger current flowing through the other two leads. The goal of this video is to show you how a transistor can be used as a switch. I'll explain the basics of a transistor and how you can use the transistor to turn on an LED or other electronic device. The name transistor was formed using the words transfer and resistor, which was combined to form the word transistor, which was the idea of describing the basic amplifying action produced by transferring a current from a low to a high resistance circuit. Commonly, a transistor is used to switch on or off current, voltage, and it can also amplify AC signals, invert signals, and is used in the construction of integrated circuits and or microprocessors. There are various types of transistors, which include the bipolar junction transistors, which is broken down into the NPN and PNP transistors. There's also field effect transistors, which is further broken down into the JFET and the MOSFET transistor, and then each one of those are broken down into the N channel, P channel for the JFET, and also the depletion enhancement mode for the MOSFET transistor. There are some other specialty components that are considered transistors as well, including the phototransistor, the unijunction transistor, and the thyristor. Now, instead of just diving in and showing how to connect the transistor up as a switch, I would like to cover how the BJT is constructed, cover the schematic symbols, and how it operates. There are other various transistors that I mentioned previously, but I will specifically focus on how the bipolar junction transistor functions. The field of transistor operation is actually a very involved field, but I'll try to make this as simple and painless as possible. The transistor is constructed as a three-layer semiconductor sandwich. The various layers are chemically doped to vary its conductivity, resulting in a change in resistance. Depending on how the layers are doped, the resulting layers are referred to as the N-type and another layer known as the P-type. The BJT comes into two forms, the NPN on the left and the PNP transistor on the right. These transistors differ in the manner in which they are used in circuits. The three layers of the bipolar transistor are the collector, the base, and the emitter. Here is the schematic symbol for the NPN transistor. Side by side, you can see how the schematic symbols differ between the NPN and the PNP transistor. Some people actually use memory aids in recalling which way the arrow points, such as NPN not pointing in or PNP pointing in. Bipolar transistor operation. The BJT essentially acts like a current control device. Here, conventional current flows through the NPN transistor as shown. A very small current applied to the base will cause a much larger current to flow in the other two leads. Once again, you can see how conventional current flows through the NPN and the PNP transistors. The arrows point in the direction of conventional current flow. You can't just apply any voltage or current to the base of the transistor and expect it to work. Internal to the BJT transistors are internal diodes that require around 0.7 volts in order to forward bias the diodes and allow the transistor to operate, essentially switching it on. The base of the NPN transistor needs to be connected to a potential voltage to allow current to flow into the device and be high enough to forward bias the internal diode, while the PNP works in the opposite manner, requiring current to flow out of the gate and be high enough to forward bias its internal diode. Either way, the middle layer acts like a valve or gate that controls the current moving through the three layers. Here is a simplified model of how the NPN transistor works internally. Once a voltage that is 0.7 volts or higher is applied to the base of the NPN transistor, the transistor will switch on. Now, the ratio between the applied base current and the resulting collector current is dictated by the gain or beta of the transistor. Typically, the DC gain can vary between 30 and 300 based on various conditions. For example, a device with a beta of 200, it results in a collector current that is 200 times the magnitude of the base current. Just to let you know, the BJT operates in 3 regions of operation. This includes the cutoff region, the active region, or the saturation region. You get the transistor to work in the proper region by connecting it up in a certain way in the circuit. There are also 3 ways that the transistor is connected in a circuit. This includes common base, common emitter, and common collector configurations. Keep in mind, too much current or voltage may damage or permanently destroy the semiconductor chip that forms a transistor. The transistor may become hot and operate improperly. If the chip isn't harmed, its tiny connection wires may melt or separate from the chip. Never connect a transistor backwards. Things to keep in mind are the max electrical properties of the transistor. Look up or be aware of the limitations of the transistor before you use it. Alright, so here is a simple circuit that you can wire up to activate an LED. It uses a commonly available NPN transistor. The transistor being used is a 2N2222. This transistor can handle up to 800 milliamps and can operate at up to 30 volts, which covers many situations. There are other transistors out there that can handle much higher current and higher voltages, but we will just stick with this one for right now. Here is a schematic for the circuit. In order to determine the components of the circuit was designed to be forced to saturate at a known current. Because the circuit was activating an LED, the current was prevented from going higher than 20 milliamps. A simple way to calculate the required base current is to assume the transistor is acting like a closed switch. We will use the simplified model to calculate the required base current. You'll need to supply the output with the correct power supply, then subtract the voltage needed from the source to the power the new device. Then the difference will be the voltage drop across the unknown resistor. Now, depending on the max current your device needs, you calculate the required resistance needed. In our example, the output source is 5 volts and the LED requires about 1.9 volts. You take 5 volts, subtract the 1.9 volts, that equals 3.1 volts. This voltage will be the voltage drop across the resistor. The LED will now need to be supplied with a current close to its max to maximize the light output, which will be 20 milliamps. Now, with 3.1 volts divided by 20 milliamps, that's equal to 155 ohms, which will be the resistor that we use in the circuit. Now, if you take 20 milliamps divided by 100, you'll get 200 microamps. 200 microamps is what will be needed to make sure the transistor saturates or is fully activated. Using a typical gain of 100 is significantly less than the actual gain of the transistor. According to the datasheet, as I mentioned earlier, the gain is between 30 and 300. Using a gain of 100 almost always gets a transistor to saturate or become a switch and pass all the current necessary to drive the load. Another technique you can use is to assume the transistor can only amplify the signal by the minimum gain of 30. This will guarantee success, but not always be ideal if you want to conserve power, especially if you have a battery-operated circuit or project. Now, the input to the transistor is calculated in a similar fashion. You supply the input with 5 volts, subtract the turn-on voltage of the diode, and the difference will be the voltage drop across the input resistor. In our case, it will be 5 volts subtract the 0.7 volts, which is equal to 4.3 volts. Now, with the 4.3 volts, you divide the 200 microamps, which is equal to a 21.5k ohm resistor. So in our case, we'll make sure that the transistor saturates by installing a much lower resistor, which results in a higher current. In our case, we will install a 10k ohm resistor. By the way, the other resistor can be ignored. It is simply in place to prevent the transistor from having a floating input by forcing the input to ground when the switch isn't being pressed. Now here is a relay being controlled with a switch. As the switch is pressed, you can see the mechanical arm in the relay opening and closing. Relays are often used in thermostats, vehicles, automation equipment, and other various devices. This relay requires 12 volts and consumes 76 milliamps of current. The relay is activated using 5 volts and only 1 milliamp of current by using the transistor and the switch. Here is the schematic of the circuit. The circuit analysis is very similar to the previous circuit in the video. The difference with this circuit as compared with the previous one is that there is no resistor in line with the load. The load in this case is the relay, as with the previous circuit it was the LED. The relay uses almost the full 12 volts. The resistance of the coil regulates the current along with the transistor. The relay also has a diode preventing back EMF as well. If you like this video, please like and subscribe. If you would like to see how the transistor can be used with an Arduino in a future video to switch on a relay, please let me know down in the comments below. Also, just to let you know, this is my very first video on YouTube. I do appreciate any feedback that I do receive. I really enjoyed putting this video together, and I hope you enjoyed it as much as I have. Thanks for watching.